Okay, so I guess one more minute and then we get started. Let me see, what do I want to look at? Hold on. Yeah, okay. So I got this for chapter 3. Fine. So will you please, all of you, display your web cameras? Oh, by the way, I sent an email asking for volunteer, and I only got one response so far. I want to set up a lab for the AC motors, and we are going to start today at 1 p.m. So I already have one volunteer. I need a second volunteer today at 1 p.m. But if you send an email, wait for confirmation. As soon as I finish the class, I will respond and give you a confirmation if there be a room for you or not. Okay. So then, so today we are going to go on chapter 4. And if you look at, so let's start looking at the material from the book about chapter 4. Now, the reason that I'm going for chapter 4 already, it is because we are going to dedicate later on some more time to chapter 3, the motors. I plan to do two sessions on lab for motors, one for AC and the second for DC. So we'll come back to motors later on as soon as the handouts are ready. Okay, and then we'll discuss the handouts and the experiments. So that's why we are jumping now to chapter 4. And there are going to be two homework which are due on Saturday, last day of January, this Saturday, on chapter 4. Okay, so then let's look at chapter 4 here. What is it? Hold on. This is, okay, this is, I need to share the document. Fine, so share document. Okay, screen 2. Okay, now here, so let's see. Chapter 4, 3.7, figure 3.2. And this one, it says, let me hold down here. Okay, so we start with figure 3.1. Okay, so this is figure 3.1 of the book. So one natural detector, light illumination detector, the comparison between the eye and the camera. Okay, so let's move forward to the next figure. Okay, so in some of the in one of the homework, be asking about the electromagnetic spectrum. So on the top figure, we see it's not very good quality, but I hope you can make out of it the visible range. Okay, and then on the second band, we see an expansion of the visible wavelengths from violet to red. Okay, and that's the one that is most blur. And then on the bottom, we have spectral continuous spectrum from the sunlight. And then we see that the light that we get from the sun peaks in green, around blue and green. Okay, so that's the peak intensity. And then it drops down to short wavelength on ultraviolet, and then it drops down to long wavelengths in infrared. Now, there are some line spectrum there at the bottom, those vertical bars, and they correspond to lamps, illumination from lamps. One of them may be a mercury lamp. Okay, so let me look at that graph in the book. Now, this is what, chapter 3, chapter 4? No, this is chapter 3. Yeah. Mercury. Okay. So the next one is, okay, look, I love this picture, okay? Because it's very clear what the radian is. So radian, that unit of angle, comes from antiquity, from all ages. So the radian is the angle of a sector in length equal to the radius r. So on the top figure, we see that the arc length is equal to the radius. So therefore, that angle is spanned by an arc of 1 radius is exactly 1 radian. So that's a nice definition. Now, on the bottom figure, we are talking about in 3 dimensions. So then the angle now becomes a steradian, or solid angle. It's called a solid angle. And then, as you can see, the spanning in 2 dimensions, or in angle theta and angle phi of spherical coordinates, are also 1 radian. And therefore, the area, the surface on a sphere span, is also going to be 1 radius on 1 dimension and 1 radius on the second dimension. What radius are we talking about? The radius of the sphere. Okay, the radius of the sphere. So then that angle becomes the steradian. Okay. Now, here comes one of the fundamental definitions of illuminance. That is the lumen. Okay. So we see a point source on the left, and that point source has an intensity of 1 candle. 1 candle. Therefore, the luminous flux emitted from that source flies away and intercept through the sphere, and at one radian, sorry, at one steradian angle is going to be a lumen, okay? Now, in this graph, we see how the, now we are looking at the same lumen emitted from the source through one steradian. So the flux is one lumen. However, the quantity intercepted by each of those surfaces at different radius is going to be called the foot candle, and is being represented by letter E. Letter E is for illuminance. So the illuminance is going to drop down because it's the same lumen all along, however, intercepted larger areas. Therefore, to get the illuminance, we divide the flux in lumen by the area. Okay. So therefore, for the first area, we have at 1 foot distance is going to be 1 foot candle. For the second area, at 2 feet away, now the total area is 4 feet square. So now we have 1/4 of a foot candle. For the third area, which is at 3 feet away, now the total area is 9 feet square. So therefore, the illuminance is 1/9 of a foot candle. Okay, so let's recap. From the source, it goes out 1 lumen per steradian. So the source can be characterized by lumens, okay, per in the solid angle. So how many lumens go out? That's the source property. Now, we have detectors, light detectors. It can be our own vision at different distances. And therefore, for those, now we talk about illuminance. And the units are foot candles. Okay. Now, the bottom figure at the bottom, we see the incident light coming to a surface which is tilted at an angle theta. Okay, so then there is going to be an illuminance dependence on the angle theta. Okay, and that's called the cosine law for incidence. All right, so then let me move to the next. So here is the analysis for the illuminance. The illuminant depends on I, the intensity, which is emitted from the source, okay? And therefore that I will be the lumens. And now we have the horizontal with the cosine. So that's the flux through the horizontal surface at the bottom. But then there is also a vertical surface, which is shown at the right. And therefore, we have a flux through the vertical surface, which is going to depend on the sine. So we have the usual dependence on cosine and sine, but also the distance square. So the distance is the hypotenuse. So that's the distance between the detector and the source. So then we have these formulas which are called the square law, the inverse square law. Okay. Now, this is a graph of intensity distribution, and imagine that circle at the center to be like a cross-sectional of a tube. For example, if this could represent a a tube that we use for lighting in the normal luminaires, fluorescent lights, for example, and then that's the polar plot is the illuminance, and it gives us the intensity as a function of angle, and it also gives so we have two coordinates, the distance and the angle. The distance is going to be 400, 600, 800. That is going to be the illuminance in foot candles. Okay. So as we can see here, the light source emits vertically upwards. So, okay. So this is the intensity distribution, illuminance distribution of a light source. Okay, so is there something else? No, okay, so questions, these are the questions. So for the homework, you are going to answer some of these questions, okay? And then let me tell you which questions are going to be for the homework. Hold on. Question 6, what is infrared energy? Question 7, what is ultraviolet energy? Okay, so those are the bands of the spectrums that become invisible to the human eye. Okay, infrared for longer wavelengths and ultraviolet for shorter wavelengths. Another question is number 9. What is the unit? Why is the unit lumen the same in both the English and the System International of Measurements? Okay. So then this question, let me bring out the other camera. I'm going to cut out this. Okay, now let me okay, so then it says we have the one candle is the unit of intensity. Then 1 lumen is the unit of flux. So let's call this I. So then let's call this 1 lumen is equal to 1 candle over 1 ster radian. Okay, and then we have 2 units now for, we have the foot can FC or the lux. These both are units of, both of them are units of illuminance. Okay, so one of them is E, the flux. So phi is the flux divided over the distance square. Okay. So if we have, let me show you this picture on here on the this one. This is a very, I love this picture. So we have one candle here, okay? And then this is a solid angle, 1 steradian. This solid angle is steradian because as you can see, the area is 1 foot times 1 foot. Okay, so then we can also define solid angle, and so what's, okay, area on a sphere equals r squared times solid angle. Okay, so if we use the we can do this for spherical coordinates. Yes. So therefore, if the solid angle is 1, area is equal to r squared if the solid angle equals 1 steradian. So that's what we are seeing here. Okay, here we have a solid angle equal to 1 steradian, and therefore the area is going to be, for the first intercept, just 1. Okay, so the question was here, number 9. Why is the unit lumen the same for the English and the SIR measurement? So it says here, why do we use the same unit for flux, the lumen? Yes, that's the question. So we have one candle at 1 feet, or we can move away to 1 meter. So in fact, 1 meter is equal to 1 over 0.348. So 1 meter is equal to the inverse, and that number is 3.28 feet. Okay. but the lumen still goes out over the same, right? So here we have one lumen, and here we also have one lumen. The lumen doesn't change. So what changes? What it changes is the intensity. So here we have one foot candle, and over here we have one lux. This is called one lux for the metric unit. Okay. So in order to do that, to calculate, we must divide by distance square. Lumen over distance square. Okay. So that's 9. The next question is going to be, let me,
Dr. Ramos.
yeah.
So the lumens doesn't depend on distance?
What?
So it doesn't depend on distance, the lumens?
Yeah. The lumens, you just look at the luminaire, and you surround the luminaire by an imaginary surface, and the lumen is what's going out of that luminaire per steradian. Yes, so when you think about the lumen, think about the luminaire. Now, when you think about the lux, the foot candles, or the luxes, now do not think about the luminaire. Think about the, for example,
How many lines are hitting the
the
surface?
table. If you want to check the flux on your table, then you think about the detector. How many what illuminants arrive at the object that you want to illuminate. Okay, does that make sense?
Yes.
So when you want, excuse me a moment. Let me. So when you buy luminaires in a store, if you go to your favorite store and you want to buy luminaires, then look for the lumens, not only the watts. Also look for the lumens of the luminaire. Okay. Later on, if you want to replace that luminaire with a more efficient luminaire, then you go back to the store and look for the same lumens with less watts. So that will make the lamp, so then you will get a lamp which is more efficient. Same lumens, but less watts. Okay. So that's question 9. Then the next one is question 11. So now question 11 asks you the relationship between the lux and the foot candle. So both of them are units of illuminance. One is, so now for the question 11, you need to calculate the areas involved. at a distance of 1 foot and at a distance of 1 meter. Okay, and then that's going to be same lumen going out, but detected at different distances. So this gives the foot candle, that's the name of the unit, and this gives the unit the lux. Okay, so which one is stronger? Which one is higher? Okay, the foot candle is going to have more illumination because it's
Smaller.
closer to the source. So a foot candle is going to be greater than the lux because the lux is far away from the source. Okay, so then that's question 11. You need to find out that conversion. And then the last question is question 16. The intensity distribution curve, and that curve is this that we are talking about. That's the tip. That's the curve that we are talking about. Okay, so you do the reading in chapter. This is chapter 3, and you can answer these questions. And now, okay, so then let's look at this. This is a summary. So let's look. Poor lighting can seriously affect your ability to perform efficiently. Of course, your response to seeing environment is very individual. Okay? Light is the portion of the electromagnetic spectrum to which your eyes respond. Okay, let's read through this and then I'll make a comment. The response of your eyes. Okay, so at the bottom, we have these 4 important units of light: the candela, the lumen, the lux, and the foot candle. Okay. Now, the third, see, where does it say it's individual, subjective? So it says at one point that we have subjective. It depends on the viewer. And let's say objective. Okay, so this is called radiometric, and this is called flux light. What's the name? Radio photometric. Look, we have different. We have here a division of unit, radiometric. So how do we measure radiation? Okay, this is called from radiation. So remember from electromagnetic, the pointing vector E cross H, the electric field times the magnetic field. So what do we have here? Watts per square meter. Now in photometric, we don't know, we use these other units. We use the lux, lumen per square meter. So then the question is, this is difficult for me to understand, but why? Then what is the equivalence between lumens and watts? And what is that equivalence? Okay. So then it turns out,
Dr. Ramos,
yeah.
is it like efficacy or something?
Can you
Is it efficacy?
efficacy in a way? Yes, but different sources have. Yeah, this will take us to efficacy of the source of the source. So then let me bring out the second page. Lecture. So this is lecture 4B. So the most efficient light source, most efficient light source has the following conversion. 1 watt can produce 683 lumens. Okay. I have never found out where do they get this number from, but that's the number it goes. Then we'll see next, depending on the lamp, we have this efficiency you were talking about, lumens per watt. Okay, the ideal the ideal lamp, 683. A 200 watt incandescent has 20 lumens per watt. These are all numbers from the book. A 400 watt mercury lamp HID, high intensity discharge, has 50. A 40 watt fluorescent FC, these numbers come from the book, okay, has 70. Okay, and so on. So now we have the LED. how many lumens per watt. So here we are going up in efficiency, right? So here we are looking at watts electric. Right? So imagine, therefore, you have your two wires through a watt meter, and then here you have your lamp, and then here you have your detector. Lumens going out. In where? In the solid angle, or total lumens. If you integrate over the sphere, then so for the lamp, for the whole lamp, we'll probably integrate over, so for the whole lamp, we integrate over complete the sphere, lumens over 4 pi square radians, sterradians, 4 pi being the solid angle of the sphere. Okay, so then here we have the conversion, right? Lumens per watt. This watt here and these lumens there give us this efficiency. So it makes sense. What it doesn't make sense to me, and I cannot give you the answer, is where do they get this number from? I never found out. I looked for it. Okay. So now about the problems. Now you can also have some problems on the book. No, but before that, let's do this exercise. Hold on, I have something here. Okay. I don't know if this page that I'm going to show you is in the, so these are some exercises. Chapter 4, chapter 3 or 4? We are in chapter 3. Okay, so if you work in solar energy, then you use watts per square meter. If you work in photometric, then you use the lumen per square meter. Both of these obey the square law. The square law says that the intensity is equal to the lumens or watts divided by the distance square. So look, here I imagine this. We know that outside the atmosphere from the sun, we get this number of watts, 1,353 watts per square meter. And this is at 149.6 million kilometers away from the sun. So we get this amount Yes. So that's why they say that in one day we get more energy, the Earth gets more energy from the sun in one day that all that we use, everybody, the 7 billion inhabitants in 1 year. Okay? It's a tremendous amount of energy. So far from the sun, and we get this amount. So we want to, the inverse square law says that this intensity is a constant divided by the distance squared. So the first step is to determine the constant K. So we have data. I is 1,353. Distance is 149.6 million kilometers. So calculate K, and then K, it comes out to be uh, this, a large number, 25. Okay. Now, once we determine K, we can determine the intensity of radiation at the different distances. So, for example, planet Venus, which is closer to the sun, what is going to be the intensity at planet Venus? So it's going to be higher than 1,353. So it can be either 1,800 or 1,500. And it comes out to be, let me see, Venus. Or look at that, there is one more here, 2,000. It comes out to be this. Venus, okay. So Venus has so much more intensity of light that's why it became hot, and it be impossible to sustain life because the atmosphere became polluted by the emission of CO2 and all these other chemical compounds which have greenhouse effect. But the driving force is the temperature and the intensity of the radiation coming from the sun. Next, we go to Mars. Mars is, okay, so 228 instead of 150 is 228. So that's further away, about 50%. So now the intensity is going to be, I could calculate this as, what is it? 1353 multiply by, then we put the square here, and then we put in the numerator 149.6, and we put in the denominator the new distance. So that number, if you calculate that number, it's got to be less than 1,353. So it'd be A, B, yeah, A or B, one of these two. And it turns out to be B. So if you work for a space company that are trying to send equipment to Mars, then your solar panels need to be more numerous, more panels, because the amount of radiation, of the intensity of the radiation is lower. Okay, the radiance is called in solar jargon. Okay, now let's look at this exercise now. So here we have, it says 2 point sources, 1 and 2, equals intensities, candelas, horizontal surface, and here are the geometry, 5 meters away. Now we are looking at this point here. So here is our detector. Okay. Calculate the illuminance in luxes. Okay, so why don't we just hold on. So the formula that we need to use is this. E is going to be I cosine theta over d squared. Okay. So let's see, I is equal to 2000. So if we come in direct, it be 2000 divided by 5 squared. So that's 2000 divided by, it be 80 luxes. If we would go direct, 80 luxes, but it's not going direct, it's going through an angle. So then we need to calculate this angle. So that angle is, I think, 4 divided by 5. Okay, yeah. And now the sine, inverse sine. So we get 53.13 degrees. The cosine, now we need to multiply by the cosine, which is 3 divided by 5, so times 0.6. Okay. Okay, so this number we said it was equal to 2080. That's in the case of straight radiation, vertical radiation, coming like this. Okay. Now this is from one light source only. We are talking about source one. So then this is the answer. This is the answer. Now, from the other source, it's still the same direct radiation, 80, but now the angle is different. So now the angle is going to be 3 and 5, 59 degrees. Cosine is smaller. So instead of 48, then the next number down, it should be this, 30. Or what? In looks, I think I got something. Yeah, that's correct. Now both of them combine. So I think we can just simply add them, right? 48 plus 30, 78.3. Okay. It's right here. Okay. So then if you go to the, let me show you something else now. So what do we want to see now? We want to see the homework. Okay, so let's show the homework. It should be here. Okay, so let's do here. Thank you. Now assignments. Okay, so these are the assignments that you have. Today is the deadline for 4Q. And then Saturday, deadline for chapter 3 questions and problems. Okay. So problems, these are 2, 4, 6, 8A and AB and 10. Okay, so homework problems 2, 4. Okay, so then let's look at this. So let me start this test. Okay, again. Begin. Okay. So we got an integer number. Chapter numerical. Okay, read at the top. Test information. Numerical responses only. Type in real numbers without units. So we just need to write the answer. So in the first problem, total lumens. So we have a room 15 feet by 30 feet, has an average illuminance, foot candles, 50 at the workplace. So we are given the illuminance, and we are given the area. We can get the area, right? The area is 15 times 30. So what is the illuminance? No, the lumens, total lumens. That's the flux. So that flux is going to be the multiplication of foot candles times area. Okay. Now, the next question is the illuminance of a surface normal to and 5 meters away from. So we have a surface 5 meters away from a light source, and we are given the illumination 360 lux. So calculate the same illuminance if the surface is moved 5 meters farther away. Okay, so here we only have data in luxes and distances, and we need to calculate the new luxes for the second distance. So the relation from one to the other is going to be the square of the total distance. So for the first, the distance is square is 25. And for the second case, the distance square is 100. Okay, so therefore the object move away 4 times in intensity, decrease in intensity 4 times. That's 10 to 5 square. Okay, so that goes, the argument goes like that. In question 4, we have the intensity of the source in candles, and then we have those numbers, horizontal and vertical, and we need to calculate the illuminance. Okay, so in foot candles, we can just write 10,000, and then we need the cosine. In case the first question is cosine horizontal, the second question is vertical sine. The distance square is going to be what is the distance square? 12 square, that's 144 plus 64. So we need to do some calculation of the hypotenuse square. That's going to be the distance square. For problems 8, sorry, question 4 and 5. Finally, the last one, 500 watt rated 10,000 lumens. Determine the mean spherical candle power of the lamp. So we have, well, maybe just the division, no? 10,000 divided by 500, what is that? 20? But it says spherical. So what does it mean by spherical? Well, something that we can do with those two numbers is divide them. I don't see more information there. Fine. Okay, so I think that's all for today. So did you write your names on the roster? Let me take the roster. So I want to show you the roster before we go, so that you can look at. Hold on, we still have some time. I want you to see the roster. I'm not going to call roll. I just want to show you the roster so that you have some input, sorry. Hold on. Okay, now we can do it. Okay, so that's what I have for roster, okay? All right. Well, thank you very much.
Thank you, sir.
Yes, class dismissed.